The topic of our lecture today is the chain rule. Our goal is to introduce the chain rule and learn how to use it. Here's our plan for the next 15 minutes. First, I will show you the situation where we will need an additional differentiation technique. Then I will formally state the chain rule, and then we will work our way up from very simple problems to more challenging examples. Let's get started. The differentiation techniques obtained so far do not enable us to differentiate functions such as radical of 1 plus x squared or sine x cubed. We could differentiate 1 plus 2x to the 12th, but only with great effort, by first expanding 1 plus 2x to the 12th to form a polynomial of degree 12 and then differentiating that polynomial. Today we will develop a shortcut for differentiating composite functions which are built up from simpler functions. The chain rule states that if a function g is differentiable at a point x and the function f is differentiable at a point y equals g of x, then the composite function f of g is also differentiable at x and f of g prime equals f prime of g of x times g prime of x. This formula looks complicated. Let's take a moment to see what we need to do to find the derivative of f of g of x. Here f is the outside function and g is the inside function. We need to differentiate the outside function f first and leave the inside g of x alone. Then multiply by the derivative of the inside g prime of x. The verbal form of the chain rule is outside prime of the inside times inside prime. Now let's look at our initial examples. The first example was a radical. We need to differentiate h of x equals radical of x squared plus 1. Here the outside function is f of y equals radical y. The inside function is g of x equals x squared plus 1. The derivative of the outside, f prime of y, is 1 over 2 radical y. The derivative of the inside, g prime of x, is 2x. The chain rule gives that h prime of x equals h prime of g of x times g prime of x. F prime is 1 over 2 radical of the argument. So, it is 1 over 2 radical of g of x times g prime of x. Now let's substitute x squared plus 1 for g of x and 2x for g prime of x. We get 1 over 2 radical x squared plus 1 times 2x. After simplifying, we get the final answer, x over radical of x squared plus 1. Our second example is a trigonometric function. We need to differentiate h of x equals sine x cubed. H prime of x is sine of x cubed prime, where the outside function is the sine, the inside function is x cubed. The derivative of the outside function is cosine, and we need to leave the inside function alone. Here is x cubed. And then we need to multiply by the derivative of the inside function. Derivative of x cubed is 3x squared, so times 3x squared. Therefore, the derivative of sine x cubed equals 3x squared cosine x cubed. Our third example is a polynomial. We need to differentiate h of x equals 1 plus 2x to the 12th. H prime of x equals 1 plus 2x to the 12th prime. Here, argument to the 12th is the outside function, and 1 plus 2x is the inside function. The derivative of the outside function is 12 times the argument to the 11th. We keep inside untouched, so we write 1 plus 2x. Now we need to multiply it by the derivative of the inside function. In this case, it is just 2. After simplifying, we obtain that 1 plus 2x to the 12th prime equals 24 times 1 plus 2x to the 11th. The derivative of f of g can be written in Leibniz notation. Recall that for any function h prime of x in Leibniz notation is dh over dx. Let's denote g of x by y. Then d over dx of f of g equals df over dy times dy over dx. This is the formula for the chain rule written in Leibniz notation. And in this way, it is a much more suggestive formula. If the symbol dy had meaning by itself, it would look like as if the dy's cancel. Our next example is a nested chain rule. We need to differentiate h of x equals radical of x to the 4th plus 2 plus 1 cubed. To find the derivative of h, we proceed stepwise. H prime of x, which is d over dx of the radical of x to the 4th plus 2 plus 1 cubed. Here the outside function is the argument cubed. So the derivative is 3 times the inside squared. Now we just need to multiply by the derivative of the inside function. In the next step, we keep 3 times radical of x to the 4th plus 2 plus 1 squared and take a derivative of the inside, which is radical of x to the 4th plus 2 plus 1. We distribute d over dx to the sum and get derivative of the radical of x plus 4 plus 2 plus the derivative of 1, which is 0. Now we need to keep 3 times the radical of x to the 4th plus 2 plus 1 squared and take the derivative of the radical of x to the 4th plus 2. We need to use the chain rule again. Now the radical is the outside function and the inside function is x to the 4th plus 2. The derivative of the radical is 1 over 2 radicals x to the 4th plus 2. And again, we need to multiply by the derivative of the inside. In the next step, we keep the expression we have differentiated already and take derivative of x to the 4th plus 2. Derivative of x to the 4th is 4x cubed and derivative of 2 is 0, thus we need to multiply by 4x cubed. After simplifying, we get the final answer, which is 6x cubed times radical of x to the 4th plus 2 plus 1 squared divided by the radical of x to the 4th plus 2. Our next example is a function with parameters. We need to find the derivative of h of x equals ax squared plus 5 to the n, where a is a positive real number and n is a positive integer. Here the outside function f of y equals y to the power n, and the inside function g of x equals ax squared plus 5. Since the derivative f prime of y is ny to the n minus 1, this is just the power rule, and g prime of x is 2ax, because a is a constant, we get that h prime of x equals n ax squared plus 5 to the n minus 1 times 2ax. Our last example is differentiating a function that is not specified. Suppose that we know the derivative of f. F prime of x is 3x minus 1, but we do not know function f. We need to find d over dx of f of x squared at x equals 2. Here the inside function is y equals x squared. The outside function is f of y. The chain rule gives that d over dx of f of x squared equals df over dy times dy over dx. df over dy is f prime, and dy over dx is the derivative of x squared, which is 2x. We know what the derivative of f is. F prime of y equals 3y minus 1. Substituting x squared instead of y in this expression, we get 3x squared minus 1 times 2x. Now we just need to plug in x equals 2 and get 3 times 2 squared minus 1 times 2 times 2, which is 44. This is the end of our lecture.